So there's the picture. It tells us that it's an isosceles triangles. And the base is 2, the height is 3, and that's when it's full. But water is being emptied, siphoned out means emptied, at a rate of 2 cubic feet per minute. So remember, cubic feet is volume. So what they gave us there is that dV over dt, and the water is leaving, so that's going to be -2 cubic feet per minute. So that's what they give us is the volume. And what else? Okay, so part A said find the volume when the trough is full. So this is an isosceles or a triangular prism. So how do we find volume of a triangular prism? Is the volume of the base times the height. And the base is a triangle, so 1/2, I'm going to call it the little b times the little h times capital H. So the little b would be the base of the triangle, and the little h, so this would be v equals, whoops, yeah, 1/2. The base here is 2. The little h is the height of your triangle, which is 3. And the capital H is the height of your prism, which is the distance between the two triangles, which is 5. So that gives us 15. So the answer to part A is 15 cubic feet. All right, B, they want us to find the rate of change in H. So dH over dt when the volume is 1/4. So volume times 1/4, which would be 15/4. Okay, so up here we have this formula for volume of our trough. So let's analyze here what's happening. As water fills up here, as it rises or goes down, this distance, this is going to change. Whether I was down here or if I'm up here, those are different lengths. What's also going to change is that height here, the height to the water. So depending on where you are, that changes. But this 5 is not going to change. It's going to remain constant no matter how, as the water empties. So when we do that volume equation for part B, so we have volume equals 1/2 little b little h times capital H. So the lowercase b and the lowercase h do change, but the distance between of 5 does not change. So our equation for volume is 5/2. Let's go ahead and multiply. 5/2 b times h. And so I have two different variables here, b and h. So if I was going to find the derivative, I would have to do product rule, but I try to avoid that. So I'm going to go and see if there's a way to find b or h in terms of the other. And I actually, since I want to find dH over dt, I'm going to look for changing it in terms of h. So we have this, if the water's full, or if the trough is full, this is 2, and this is 3. Well, it's not always full, it's being emptied. So if I draw another triangle, this is B, and this is H, because those are changing. So I have these two triangles where I can set up proportions. So I can say B is to H as the whole thing is to the whole thing. And so I have 3B is equal to 2H. And so I wanted it in terms of H. So B is going to be 2/3 H. So down here in my volume formula, instead of B, I can change it to 2/3 H. So here I'm going to put 5/2. And instead of B, I'm going to put 2/3 H. And then I have that other H. And now I can simplify this. So I get 5/3 H squared. And then finding the derivative is a lot easier. I don't have to do product rule. So dV over dt is equal to 10/3 H times dH over dt. And they gave me dV over dt, remember, was -2. So this is -2. 10/3. I'm looking for dH over dt. So that means that I should be able to find this H somewhere. So let's go back up to what did they give me? So we're finding it when the volume is 14/3 or 14/4. So remember our equation for volume. So I'm going to set 14/4 equal to 1/2 the, oh, let's use this volume formula here. Let's use this one right here. So my volume is 15/4. That makes it a lot easier. So then H squared is equal to 9/4. So H would be 3/2. We don't need plus or minus because we're talking about dimensions. And so now I know that this H is 3/2. And so let's go ahead and solve for dH over dt. So -2 equals, those 3's can cancel, so 5 dH over dt. So dH over dt is equal to -2/5. I'm going to put it over here so I can fit units on it. So remember, it was measured in cubic feet, so feet, and the time was minutes. So this is height, so it would just be feet per minute. And it should make sense that it's negative because remember the water was going down, so the height is changing at -2/5 feet per minute. All right, that was a hard part. All right, so part C, find the rate of change in area of the surface of the water. So the shaded region. So the shaded region here you can see is a rectangle. So for part C, we're finding the rate of change in area of that rectangle, which is, go back up here. Remember that 5 is 5 no matter what, but this dimension of base is changing. So this we're going to write as 5 times B because B is changing, but the 5 is not. So now when we find the rate of change in area, it's 5 times the rate of change in the base. And I don't have the rate of change in the base. So I have the rate of change in the height. So we might need to come up here, and instead of using B, let's go use what B is, 2/3 H. So I'm going to change this over here. So I'm going to say that this is really 5 times 2/3 H. So this didn't help me, so that's why I'm redoing this, because I don't have this. I don't have what that is. So I'm going to change my area formula to be 10/3 H. I just used that proportions, the triangle's proportions. So dA over dt is equal to 10/3 times dH over dt. And dH over dt we just found to be -2/5. So that's going to give us, what's that, -4/3. And its area, and area is measured in square units. So it would be feet squared per minute.